Hello everyone. Today we're going to solve some of the problems from the chapter electrostatic potential and capacitance. The problem here is two capacitors of capacitance 1 microfarad and 3 microfarad are charged to 800 volt and 400 volt respectively. So basically they have considered two capacitors. So the capacitor value is, I'll write the given part here. So the capacitor value is 1 microfarad. You cannot keep it in microfarad, so you'll write it as 1 into 10 to the power of minus 6 farad. And then second capacitor is 3 microfarad. So 3 into 10 to the power of minus 6 farad. These two are charged to 800 volt and 400 volt respectively. So they have given the potential difference across each capacitor as well. So the potential difference here is across first capacitor is 800 volt and across second capacitor is 400 volt. Okay, find the common potential difference, the charge on each capacitor. Then you need to calculate the energy dissipated when they are connected in parallel. When they ask you about energy dissipation, okay, basically it is loss in energy. So when you have to talk about loss in energy, there exists two conditions: before the connection, after the connection. So you have to calculate before the connection as well and also after the connection. So when they are since they have asked the charge on each capacitor, you have to find out the charges before parallel connection and after parallel connection. Okay, so let's find out before parallel connection, the charges before parallel connection now. So I'll take it as Q1. Q1 equals to capacitance and the potential difference. So this gives you the value of charge before you connect it to parallel. Okay, so QC1 is 1 into 10 to the power of minus 6 and then V, that is 800. Okay, calculate and get the value for first charge. Second is Q2, C2, V2. Okay, that is second capacitor and the potential difference across that second capacitor. So that is 3 into 10 to the power of minus 6 into 400. So calculate and get the value for Q1 and Q2. So I have got 800 into 10 to the power of minus 6 and then 1200 into 10 to the power of minus 6. So these are the values of charges before the connection. Okay, so now then you need to find the common potential difference. Okay, the charge on each capacitor is also fine. Then the energy dissipated when they are connected in parallel. So here I'll consider a condition. I'll just draw a diagram and show you. So here let's say this is a capacitor and this is Q1 and this is C1. Okay, let's say these are the points A, B. Here is the potential difference across first capacitor, so that is V1. Okay, then next is one more capacitor, A, B, Q2, C2. The potential difference across second capacitor, that is V2. So they have told you here they are connected in parallel. Okay, so now you are going to connect them in parallel. Let's say you have connected these two in parallel. Okay, so when you connect them in parallel, okay, so you will take effective capacitance and then you will take the total charge here to get the value for common potential difference. Okay, to get the value for common potential difference, here you need to find out common potential difference to get common potential difference, you need to have the value for total charge and also effective capacitance. So what is the effective capacitance here? So here the effective capacitance is, first we'll find out total charge, since we have already got the value for total charges. So Q equals to, this is total charge, okay, Q equals to Q1 plus Q2 equals to 800 plus 1200. Since 10 to the power of minus 6 is common, I'll take it outside, equals to 2000 into 10 to the power of minus 6 coulomb. So this is the total charge, okay. So this is the total charge. Now you have got the value for total charge. This is before connection, before parallel connection, okay. Now before parallel connection, to find the value for common potential difference, okay. Now there is effective capacitance, okay. So you need to find out the effective capacitance value. So effective capacitance value can be considered as C1 plus C2, okay, that equals to C1 is C1 is 1 into 10 to the power of minus 6 plus 3 into 10 to the power of minus 6. So that equals to, what is the value again? It is 4 into 10 to the power of minus 6 farad. So you have got the value for effective capacitance and also for the total charge, okay. Now can you find out the value for common potential difference? Yes, you can find out the value for common potential difference now, okay. The value for common potential difference is V equals to, okay. If Q equals to CV, then what will be V equals to? V equals to Q by C. So which Q are you going to consider here? Since it is common potential difference, you will consider the total charge divided by the effective capacitance. So that equals to 2000 into 10 to the power of minus 6 divided by, here it is 4 into 10 to the power of minus 6, okay. So now it's old, okay, 10 to the power of minus 6, 10 to the power of minus 6 gets cancelled out. So what is the value which you have got here? It is 500 volt, right. So it is 500 volt. Now 500 volt is the voltage, it is a common voltage, okay. Now let's say you have connected the capacitors in parallel. So let's say this is one capacitor and this is one more capacitor, okay. The capacitor which has got value 1 into 10 to the power of minus 6 and this is the value 3 into 10 to the power of minus 6, and these are the 2 points here. When the capacitors are in parallel, the potential difference across capacitor is common, okay. So what is the potential difference across these two capacitor now? Here it is 500 volt, okay. Now you need to find out Q1 and Q2, okay. So you need to find out the value for Q1 and Q2. Let's solve the value for let's find out the value for Q1. So for Q1, so this is the charge on the capacitor, first capacitor, or Q2 is the charge on the second capacitor after you connect it in parallel, okay. So let's find out the value for Q1. Q1 equals to C1 V, okay, because the voltage potential difference across each capacitor is same, okay, equals to C1 is 1 into 10 to the power of minus 6 and potential difference is 500. So here you get the value for Q1, and then there is Q2. Q2 equals to C2 V. C2 is 3 into 10 to the power of minus 6 into 500. Again calculate and get the value for Q2. So it is 500 into 10 to the power of minus 6 coulomb. So it is 1500 into 10 to the power of minus 6 coulomb. So you got the value for the charge on the first capacitor and the charge on the second capacitor when you connect them parallelly. Okay, so now we'll find out the value for the energy. Okay, total energy of the capacitor before connection. So here I'll write U1. Okay, U1 is the energy, and then half C1 V1 square plus half C2 V2 square. So what is half as it is, and then C1 is 1 into 10 to the power of minus 6 into V1 is 800 the whole square. So this is before parallel connection. Okay, so you will write the values of potential difference from the question. Okay, so these values you will write here. Half C2 is 3 into 10 to the power of minus 6 and V2 is 400 the whole square. So calculate and get the value for U1. So U1 value is 0.56 joules. Okay, and then we'll move to the energy stored after parallel connection. Okay, that is U2 equals to half as it is. So half into capacitor into square of potential difference is the formula. Here after the connection you will consider the effective capacitance, that is C1 plus C2 you will consider here. So C1 plus C2, or directly you can write it as CP. Okay, so into V square you will consider here. You will not take V1 or V2. Okay, so after the connection the potential difference will be common to both the capacitors, so you will take it as V square. So equals to 1 upon 2, 1 into 10 to the power of minus 6 plus 3 into 10 to the power of minus 6 into bracket. So what was the value for potential difference? The potential difference value was 500, so you will take it as 500 the square. Okay, so half 4 into 10 to the power of minus 6 into 500 square. So that gives you the value 0.5 joules. Okay, so this is the energy stored after parallel connection. Okay, now we'll move to the energy dissipation part. So dissipated energy or loss in energy equals to U, that equals to U1 minus U2. What was U1? U1 value is 0.56 minus 0.5 joules, right? So what is the dissipated energy here? So the dissipated energy is 0.06 joules. Okay, so you have got the value for energy dissipated, and then you have also found the value for common potential difference, and you have got the values for charges on each capacitor before parallel connection and also after parallel connection. So this is about this particular problem. We'll move to the next problem. So the next problem is point charges of plus 2 nanocoulomb, plus 4 nanocoulomb and plus 8 nanocoulomb are placed at the corners A, B and C respectively of a square ABCD of side 0.2 meter. Calculate the work required to transfer a charge. The charge value they have given 2 into 10 to the power of minus 9 coulomb from D to the center of the square. So they have given the diagram here. So the diagram says it's a square. So it has got 4 sides. So A, B, C and this is D and there is a center to it. So this is the center O. Okay. So there is charge Q1, Q2, Q3 placed at A, B, C. So here is Q1, here is Q2 and here is Q3. Q1 value is 2 into 10 to the power of minus 9 coulomb and Q2 value is 4 into 10 to the power of minus 9 coulomb and then Q3 value is 8 into 10 to the power of minus 9 coulomb. Okay. So you need to find out the work required to transfer a charge. They have given the value 2 into 10 to the power of minus 9 coulomb from D to the center of the square, that is O. Okay, first we'll find out to find out work. What do you need? You need the charge that they have given. You need potential as well, potential difference you need. Okay, so do we know the value for potential difference? No. So first we need to find out the value for potential difference. So let's find out the value for potential difference. Okay, between VD and O, the point D and point O. Okay, so first find out the potential, the total potential, electric potential at O and the total electric potential at D. They have given the sides. The sides are 0.2 meter. Okay, so these sides are 0.2 meter. Okay, so we don't know the value for diagonal. Okay, so here the diagonal value we don't know. So when you apply Pythagoras theorem, you will get the diagonal value 0.2 root 2. Okay, so the value for half of it. So the distance from, so since the value of diagonal, that is, I'll write it down. So BD equals to AC. These are the diagonals. So the values of this is 0.2 root 2. Okay. So what will be the value for AO and then BO and then CO and then DO. So this will be half of the diagonal, that is 0.1 root 2. Okay, so this is the distance. It's in meter. Okay, now you need to find out the electric potential at the center of the square and the electric potential at D, point D. Okay, so let's first find out the electric potential at the center of the square. So electric potential at center of the square can be written as 1 upon 4 pi epsilon naught from the formula. Okay, into bracket. So you have charges at these points, so you will consider only these 3 charges. Okay, so first charge Q1 divided by the distance between center and the first charge, that is AO, plus second charge divided by the distance between B and the center. Similarly, Q3 equals to CO. So 9 into 10 to the power of 9 is the value for 1 upon 4 pi epsilon naught into bracket Q1. Q1, what is the value for Q1? Q1 is 2 into 10 to the power of minus 9 divided by, that is 0.1 root 2 plus Q2 is 4 into 10 to the power of minus 9 divided by again 0.1 root 2 plus Q3 is 8 into 10 to the power of minus 9 divided by 0.1 root 2. Calculate and get the value for the electric potential at O. Okay, so what is the value for electric potential at O? It is 891.1 volt. Okay, so this is the value which you have got for the potential, electric potential at the point O. Now the total electric potential at the point D. So we'll write it as Vd equals to 1 upon 4 pi epsilon naught Q1 divided by A D plus Q2 divided by B D plus Q3 divided by C to D. Okay, so write down the values. 9 into 10 to the power of 9. Q1 is 2 into 10 to the power of minus 9. A to D is 0.2 meter. So you will write it as 0.2 plus Q2 is 4 into 10 to the power of minus 9 divided by BD, the diagonal, that is 0.2 root 2 plus, and then Q3 8 into 10 to the power of minus 9 C to D, again the side, that is 0.2. So calculate and get the value for electric potential at the point D. So it is 577.2, 577 volt. Okay, 0.2 volt. So you got the value for the electric potential at the point, at the center of the square, and the electric potential at the point D. So you have got two electric potentials now. Now find out the potential difference. Potential difference between O and D is, so V equals to VO minus VD, potential at center minus potential at the point D. So that equals to 891.1 minus 577.2. So what's the value? So the value is 313.9 volt. Okay, so this is the potential difference. So to find out work function, you need potential difference. So you have got the value for potential difference here. Okay, so we'll find out the value for the work required to transfer this much amount of charge from the point D to O. So that is V into Q. So the potential difference is 313.9 into the charge is 2 into 10 to the power of minus 9. So the value, calculate and get the value. So the value is 627.8 into 10 to the power of minus 9 joules. Okay, so this is the total work required to transfer a charge from the point D to the center. Okay, so we have got the value for work now. I hope it helped you. I hope you have understood the problem. I'm going to solve CET related, NEET related and GE related problems as well in the channel. So please do follow the channel. Please do subscribe to the channel. Thank you.